Our last speaker is Dr. Catherine Birgitta Whaley. She is a professor of chemistry at the University of California at Berkeley. She is a physical and theoretical chemist. Her research has focused on the scattering of atoms and molecules from surfaces and quantum dynamics of atoms and molecules in clusters. Quantum dynamics of atoms and molecules on surfaces and in clusters. She will speak to us today on cold, not polled, I apologize, the accent, cold nuclear fusion, a possible theoretical explanation. Dr. Whaley.
The title of my talk is a statement that nuclear fusion reactions can occur in metals at room temperatures as a result of an effect which I call boson screening. In the short time allocated to my presentation, I want to explain what this means and also to explain what are the fundamental phenomena involved in this effect. And just by way of note, the correct spelling of my name is at the bottom here. Now, I'm not going to deal with how deuterium gets into the metal, nor am I going to deal with the products of the nuclear reaction. So I'm not going to address questions of excess heat, appearance of neutrons, etc. My only concern here is the mechanism of how any fusion reaction can take place at all in the metal environment. Let me first say a few words about the energetics and mobility of hydrogen isotopes in metal. The important species for me is deuterium. So, shown schematically here are the energy levels of deuterium in the octahedral sites in palladium, where it can rattle around in vibrational motion. Now, the classical barrier to diffusion from one octahedral site to another is 2000 degrees Kelvin. This barrier here. And the first vibrational state, above the ground state, lies at about 500 Kelvin. This means that at room temperature, which I've denoted by KT here in green, most of the deuterium is in the ground vibrational state in these octahedral sites. The large mobilities, which are seen at room temperature, are then attributed to tunneling through the barrier. And as I'm going to mention tunneling again in a few minutes, I want to repeat, this is tunneling of the deuterium through the barriers provided by the palladium lattice. Because of the periodic nature of the lattice structure, these states of deuterium, these vibrational states, can also be extensively delocalized. Now, the three isotopes of hydrogen fall into two groups as far as their nuclear structure is concerned, shown schematically here, with apologies to the physicists in the audience for molecular pictures of nuclei. Hydrogen and tritium are both fermions with spin a half, while deuterium is a boson, has spin 1. So deuterium being a boson means it's like helium-4 and can undergo condensation at low enough temperatures. By condensation, I mean that all particles go into the lowest energy level available. Now, in chemistry, we're not very familiar with both condensations because helium, which is the most common system which shows both condensation, only does this at extremely low temperatures, which is not usually relevant to chemistry. But as you see from the diagram of the lattice here, the energy level, the particular energy level structure here, shows that room temperature, KT, is actually sufficiently low to cause all the particles to drop into the lowest energy states, or the lowest group of energy states here. So I maintain that the Bose-Einstein condensation of deuterium, the bosonic species, is induced by the metal lattice. Could I have the next slide? Now we want to see how this Bose condensed character of deuterium, or deuterons, in metal affects the internuclear potential between any two deuterium atoms. And this is now the internuclear potential which normally inhibits fusion reactions. This view graph shows schematically, not to scale, shows what we mean by screening. Screening refers to the reduction in the range, and hence also in the width, of the bare Coulomb potential between two nuclei. And it's shown here as a repulsive Coulomb potential between two like positive, in this case, positive charges. This reduction of the range of the potential from the bare potential here shown as the solid line to a screen potential shown as a dotted line. If this reduction is sufficiently extreme in the range, it means that there will be a consequent increase in the probability of tunneling through this screen Coulomb barrier at room temperature, and hence an increase in the probability of having a fusion reaction.